Uh, Hi all, welcome to A3's latest webinar. So I'm just going to share my screen so we can make a start. So hopefully that's coming through. So yeah, welcome to the webinar on capturing value using carbon capture, utilization, storage to unlock value in biogenic CO2. So at A3, we've conducted more than 200 CCUS projects in the last 3 years and have been working on CCUS for much of the last 2 decades. And certainly an ever increasing number of those projects have involved biogenic CO2 rather than fossil CO2 emissions. And today we're going to be delving into that topic and sharing some of the key learnings from that body of work. So just moving through the slides. Disclaimer and rights, so I won't dwell on this one. I'll read it at your leisure. So we will be sending the slides round afterwards, so you can take an in-depth look at this one. But turning to the presenters today, so I'm Stuart Murray. I'm a director and our global head of CCUS team here at A3, based in our London office. And I've been working on CCUS projects with A3 for almost 20 years. That's with a range of governments, developers and investors, and on projects across Europe, Canada and the US. I'm joined today by my co-presenter, Katarina Lundgren. So I'll hand over to Katarina to say a few words.
Yes, hi everyone, Katarina Lundgren. I am based in Sweden. I'm section manager for our process technology section here in Sweden, working with chemicals and petrochemicals, or background in petrochemicals. And I've been working with carbon capture projects for the last 5 to 6 years from the technology side. Thank you.
Thanks, Katarina. And also on the line today, we've got 2 other A3 colleagues who will be joining us for the Q&A session later, who are our pulp and paper experts. So I'll hand over first to Ulf Strenger.
Hi, I'm Ulf Strenger. I'm working in the A3 Solna office in Sweden. I've been in the firm since 1995 and been working in the pulp and paper industry since then in different roles. Nice to see you.
Thanks, Ulf. And Dave?
Hi everyone, I'm Dave Paulson. I'm based with Stuart in our London office and working in the consulting side of the business. I've worked for A3 for nearly 20 years now, and prior to that I was working in the pulp and paper industry itself. And so nice to see everyone on the call.
So just a few housekeeping rules before we start. Hopefully everyone has managed to get in on the GoToMeeting, the panel okay. Please ask questions. There should be a sidebar there for asking questions throughout the webinar as they come up. What we'll do is we'll leave most of those questions to the end unless there's anything really urgent, but we'll cover as many of those as we can in a Q&A session at the end. So we should have about half an hour to run through the slides, and that should give us 10 to 15 minutes at the end. As I've already said, the slide pack and also a recording of this will be emailed out to all attendees as soon as they're available. So it should be within a week to get those out. So don't worry, you will receive those afterwards. And then before we start the core content of the work, we just wanted to check everyone is awake and run a short poll. So Edwin, if you could get that up, please. Great. So I think that's now being shared. So hopefully people can see that. So the question for today is which of these listed below do you believe is the current biggest barrier to CO2 capture adoption, particularly in the forest product industry? So we'll let that run for a minute or so, and then we'll capture that. So I can see we've got a good number of those on the line voted now. I think we're up to almost 3/4 of those having voted. Yeah, so very interesting, I think, the results. So key one of those being revenue uncertainty. So we'll come on to that when we talk about the commercial models, with a kind of a strong second place, I guess, from a lack of supportive policy and regulation. So we will bring that into the Q&A session at the end. We'll compare that and see if the panel agree or disagree with those. But yeah, it's certainly interesting to see those two coming up, and also the ones at the bottom, I think there. So people not seeing as much risk in the technology, access to capital, or that complexity of integrating with the existing pulp mills. Okay. So we're going to close the poll, and I'm just going to check that screen sharing has restarted. Is that right? Just looking for a nod from my colleagues. Perfect. Okay. So as I said, we'll have about 25 to 30 minutes today to talk through the slides, followed by the Q&A. We're going to talk through first the current state of play of CCUS. I think there's a lot of kind of myths out there around CCUS, so it's useful to talk about where we are in the market kind of more broadly for CCUS. Then we'll dive into the specific opportunities as we see it for CCUS in pulp mills. Talk through a few of the emerging CO2 capture technologies as well that we see, and handing over to Katarina for those two sections. And lastly, I'll kind of wrap up talking through some of the commercial opportunities, the revenues available, the revenue stacking and risks, followed by the Q&A. So on the current state of play, so here at AFRY we see CCUS and really view it as kind of, it is widely regarded, I think, as a crucial solution to reduce GHG emissions globally. And really that's four key use cases where we see it playing a large role in the net zero future. The first of those is in decarbonising heavy industry. It's not the only option, but it is one of the most promising options for many sectors like cement, chemicals, refining and metals. The second key area is on permanent CO2 removal. So we talk about that as putting the net in net zero. And so that's where you're capturing CO2, whether that be directly from the air or biogenic CO2, bioenergy CCS, and then storing that CO2. So you're removing that CO2, bringing it down. And we see that as part of many of the kind of climate scenarios, or the net zero compatible climate scenarios. The third key area for CCUS is in combination with hydrogen and power to X. So that can be blue hydrogen production. So that's one route where we see decarbonised hydrogen playing, but also crucially, and we'll talk through this later, combining CO2, particularly biogenic CO2, with hydrogen to create synthetic fuels for decarbonising the transport sectors into going to those renewable fuels markets. And the last point, which was when I started doing this about 20 years ago, this was probably the #1 use case for CCUS, but it is thought of as a bit smaller now, but it's power system support. And this is not instead of renewables, but really seeing power CCS as a real potential to complement the rapid expansion of renewables as we electrify a lot of the economy going forward. And just on the right-hand side of this slide, some of those statistics, we are at around 50 million tonnes of CCUS in operation globally today, and that's focused here on carbon capture that's being taken and then stored in the subsurface permanently. In terms of where we need to get to in 2050, the scenarios for Europe tend to land at around a requirement for 500 million tonnes of capture or of CCUS to reach net zero in Europe alone, and that's both with CO2 being put into the subsurface for storage, but also being utilised in various sectors. And then globally, you're talking about 6,000 perhaps to 12,000 million tonnes per annum of CO2 needing to be captured and utilised or stored, with the IEA 2050 net zero scenario is about 67,000 million tonnes, for example. But just to put that in context, that would give you a potential kind of CO2 capture industry of $2 to $3 trillion per year in global size, which would be the same size as the global oil market today. So there's a real kind of it shows you some of why there's some real interest from some key players in this market. So we talked about 50 million tonnes today, and this need about where you get to in 2050. So kind of taking a view in the interim, looking out to 2030. So this diagram here is showing the announced projects by region on the left-hand side. So we've excluded some very early phase speculative projects from this list, so it's not everything that's been announced. But we see that there are around 330 million tons of projects that are in various development stages. About 85% or over 80% of those are in North America and Europe. So we see those markets as kind of jointly leading in this area. Now, that includes both kind of fossil CO2 capture as well as kind of bio-based, biogenic CO2 capture. Looking specifically at bio-based, there's about 52 million tons of projects in development across the pulp and paper, some in energy from waste, biofuel, and in the power generation space. And it is worth noting that for the pulp and paper sector, we have definitely seen some movement. I think Domtar, for example, have a project announced with Svante under development in Arkansas, and then CO280 have also got a project announced in the US. But we see a lot of, even though it's a small number now in this diagram, we certainly see a lot of kind of early stage interest, strategy work ongoing in CCUS. And the expectation from AFRY's side is that we'll see a lot more of those pulp and paper projects coming forward in the coming years. So that's the global perspective, just zooming in a bit more into Europe. This time we're taking the data and cutting it down by the kind of industrial sector rather than the country. So as of today, operational as of last year, we had less than 4 million tons in Europe, and the majority of that is actually in the gas processing sector, although it's hard to read in that diagram, and less than 1 million tons of biogenic CO2 capture, primarily for use in kind of small e-fuel projects, horticulture, and other utilisation applications. By 2030, there's 114 million tons of projects, with a significant focus, for now at least, on the power and heat, hydrogen and cement sectors are all kind of leading the way. But there is more than 30 million tons of biogenic CO2 or bio-based projects that are also under development. And in terms of the status of those projects, as of 2024, we're seeing about 13% or about 15 million tons of those projects have now moved into the construction phase. So we are starting to see projects really move through from that theoretical phase and take FID. And we're certainly seeing that happen much more rapidly in the last year or so. So with that run through, I'm going to hand over to Katarina to walk us through the process and the technologies.
Great, thanks, Stuart. So we'll start about talking a little bit more about what different opportunities there are to capture CO2 from pulp mills. I'll touch on some of the traditional ways of doing it, or the more front runners, as well as emerging carbon capture technologies that we see are specifically interesting towards this industry. For capturing CO2 from any process, there are two different ways mainly you can do it: pre-combustion or post-combustion. I know there's 3 listed here, and I'll get into that. For pre-combustion, it's usually more energy efficient, but requires extensive retrofitting and changes to existing facilities. So it's not often considered as an interesting method when we look at brownfield projects or existing plants across the industries. If we look at the post-combustion option, what we do is we take the flue gases from the stack after combustion and cleaning, and the solutions are then more easily retrofitted, as the main interface with your existing plant is from the stack. It doesn't usually impact the main operations of the existing plant. And then for the third last box here at the bottom, one additional thing you can do with post-combustion is to oxify your boiler, which will give you a more complete combustion, resulting in a higher CO2 concentration of your flue gases. This opens up for less complex separation steps downstream of your flue gas, and I will touch a little bit more about that when we look at emerging technologies. So for pulp mills specifically, what are the benefits of post-combustion? There's a couple of edges that you have within the pulp milk sector. For starters, you have a fairly high CO2 concentration in your flue gases usually. This is compared to heat and power, where it can be as low as 4% and usually never over 10. And depending on the stack, we often reach up to 20% when we're looking at pulp mills. This generally means that, in general, the higher the concentration of CO2, the easier it is to extract the CO2. you normally also have fewer contaminants than, say, the waste to energy sector, which means that the cleanup steps are usually a bit less complicated. Secondly, many pulp mills have large volumes of flue gas for each of your sites compared to other industries. I do compare a lot to the energy sector here because they have at this point in time come a bit further when it comes to implementing carbon capture. But when I say large scale in the energy sector, it's still not as large as the potential in the pulp mill industry. And there's a reason why this is one of the main points here, and is that with a lot of these new or emerging technologies, economy of scale definitely plays a big part in the bankability of the projects. So it's very useful to have large volumes. The last point here is in a lot of the established mills, you have good utility systems already with various sources of heat, which could be utilized. Different capture processes consume different types of utilities, which is why there isn't necessarily a one-size-fits-all solution. But because the host sites are fairly flexible, usually you consume your utilities that you produce within the battery limit, we can usually find a solution that works. And again, compared to the energy industry, where they might have commitments to export heat or power, you don't necessarily have the same constraints here. Within the traditional or front-running technologies, I want to touch on the two that we often hear about here, and it's amine and HPC. We hear about them because they're the ones that are the furthest along in the development chain right now and get sort of the most press, so to speak. Stuart, if we go to the next one. Both amine and HPC technology falls under the category of absorption technology. This means that they use a solvent, either chemically or physically, to remove the CO2 from the flue gases. The processes that we mainly talk about, amine and HPC, are both very well known and established processes. They come from the petrochemical industry, where they've been used traditionally to remove CO2 from processes in order to vent them. That's to avoid buildup of CO2 in the plant or in the process. And although they're well known, they've definitely been reinvented slightly to fit the application of carbon capture, where the CO2 is seen as a product stream, not just a rest or a waste stream. For amine technology, we know that's being used on several projects that have recently taken FID. I think the first one will be commissioned soon, and HPC is being used in one of the projects that took FID recently. I think Stuart will mention them later as well. So it's the first time that we're seeing these technologies at large scale, and we're optimistic that they can be optimized and adapted quickly and implemented into other and larger projects in the future. Just to run through them very, very briefly without going into too much detail here. Amine scrubbing usually uses an aqueous solution and operates on a temperature difference. So the key here is that you heat up in one of the columns and you cool down in the other to absorb and desorb the CO2. The process requires a heating source. Usually that's low pressure steam. And it's worth commenting as well, for both the amine and HPC, you're introducing a chemical to your site. Amine is not the nicest chemical, so there's a hazardous aspect involved in this as well. For HPC, it works on the same principle, where you are absorbing and desorbing the CO2. This one works on a pressure difference, so you need to pressurize your flue gases up to around 5 bar, or higher, between up to 10 bar, and then depressurize them to be able to desorb them. So whereas the amine technology uses steam, this one uses a lot more electricity to compress the gases in comparison. But fundamentally, they work in the same principle of absorbing and desorbing. And again, these are the two that have been most sort of seen in the press, and these are the ones that have taken FID in some of the large-scale projects that we're seeing right now. I also wanted to mention a little bit about the emerging technologies. So I'll go through two of them here that I think are usable or applicable to this industry specifically. Whereas the other two were absorption based. The ones that I want to talk about are adsorption based, and I'm not going to necessarily go into the fundamental differences between the two, but adsorption is you fix something to a surface, whereas absorption is the two are mixed together entirely in very, very easy terms. You've probably heard of several of these already, and if we go to the next slide, Stuart, we also just want to showcase that for all of these emerging and established technologies, there are a significant number of players on the market. So it's not like you would pick one technology and be stuck with one vendor. There's a lot of room to optimize and adapt and speak to different providers of these technologies. One of the ones that is very much established is cryogenic separation. I'm sure you've all heard of the companies like Linde and Air Liquide, who deliver very large scale plants, cryogenic plants across all industries. Here, they've started adapting their flow sheets for CO2 separation specifically. So you would use a pressure swing system where you absorb the CO2 and then release it again. And then you have a cryogenic distillation unit in a cold box and you get liquid CO2 out. And that's one of the main benefits of this as well. And one of the reasons that this is worthwhile mentioning here is that this process technology specifically really lends itself to economy of scale. So the larger the volumes you have, the more the bigger a positive impact it has on the capex or the cost per ton of CO2 that you get out in this kind of system. Also, it's a benefit that you would then export the CO2 in its liquid form already, so there's no need for further liquefaction after this process. The other one, which is also a physical sorbent, MOF, metallic organic framework. This is a bit more novel, but works on the same principle as pressure swing absorption, except that it's temperature driven. So you have a big circular solid structure that spins on its own axis, and you pass the flue gases through one of the sections, and it then rotates on where the CO2 is released using steam from the next section, and then the frameworks that come in cells are reconditioned with cold air. One rotation is about 60 seconds, so it's a fast process and it's easy to ramp up and ramp down. The benefit of this system, of this technology, is that you can use low-grade heat, both for the steam side here. Usually the low-grade heat, if you have steam below 2 bar, is not really usable heat in a lot of processes, but here in this case it is. So you could potentially use waste heat from your plant in this. And just to touch briefly as well on oxyfuel. Now, the oxyfuel process itself is not really a carbon capture process. What you do is instead of firing your boiler with air, you can increase the oxygen content. You can even increase it up to pure oxygen firing. And by doing so, you aid the complete combustion in that block, which increases the CO2 content of your flue gas. And again, depending on how much you increase that CO2 content by, you could potentially cut out the carbon capture step altogether and just purify the CO2 or the flue gas stream coming out and liquefy it. So the downside of this is obviously that it's a retrofit to existing plants that interrupts one of the core processes in the plant already. So it makes more sense if you have a green field, for example. Also, the issue of getting the oxygen there. If you have an air separator unit, it's usually a big capex investment as well as an OPEX issue. If you have the opportunity to co-locate your carbon capture with a user of the CO2 that also produces hydrogen from electrolysis, you could potentially use the oxygen from that electrolysis as a byproduct to fire it in your boiler. So there is potential here. And then just for the last one, I wanted to do a quick comparison of the traditional ones and these novel new technologies. And as you can see, there are pros and cons in each, and different clients will put different weighting on what they think is important. Some people think it's very important with technology readiness, so that something is proven and has a good track record. Others find that CAPEX is more important, or OPEX even. But I think what the important take home is that even with the traditional and new emerging technologies, there are a lot of different solutions that could potentially enable carbon capture in the pulp mill industry. And we can tailor them to suit whatever needs the client has in most cases. And then I guess a question that's asked a lot is, what do you then do with the CO2 once you've captured it? And that's where I'll pass back to Stuart to answer that part.
Yeah, thanks, Katarina. That's great, and I think you've stuck exactly to time, and so we do have a few minutes to talk about exactly what we do with that CO2, and talk about the commercial opportunities. So both kind of why we're doing what we're doing, and then what choices do we have once that CO2 has been captured. So just to kind of start at a high level, so this is a very kind of high level process. So we've already talked about the CO2 source and the capturing part of this, and then kind of moving left to right through the transport, and then we have a choice really whether we go down a storage route. So CCS could be onshore storage, and that's being developed in the likes of Denmark and some place in the US, for example, and Canada, or offshore storage, which is the more common European choice currently. And if we look at the top route there, where we've got that grey dot, so that's corresponding to fossil CO2. So where you're taking fossil CO2, capturing that and storing that, well, your key driver there is carbon tax, is the EU emissions trading scheme. Sometimes that carbon tax is also stackable, so we have more kind of a higher carbon tax than just the EU ETS. And if you capture and store that CO2 rather than emitting that to the atmosphere, it's counted as not emitted under the EU ETS. We've had that since the CCS directive of 2009, and so you avoid a cost. You avoid that EU ETS cost, or that carbon cost. If we look at the line down from that, that is looking at if you capture biogenic CO2 and then you're storing that. So that you really are accessing this voluntary carbon market. So you're going through a process of certifying your CO2 that has been kind of captured and stored, and working out what the net impact is, the abatement that's occurred because of that. And then you're able to sell those certificates, and often those are being sold to kind of large corporates currently, and that gives you just this voluntary CO2 removal certificate. And in terms of the price level, if the EU ETS is trading today at perhaps 80 euros a ton, we're seeing multiples of that traded in this voluntary CO2 removal certificate market. So that's might be a 2, 3, or even 400 euros a ton, depending on your exact approach for CO2 removed, biogenic CO2 removed in that way. Your last route that we have done here is the bottom one, which we're calling kind of the physical or the liquid CO2 market. Now that can be either fossil or biogenic CO2, and sometimes we see a price differential into those markets. There is a extensive use of CO2 today. If you drive down any motorways and things, there will be CO2 trucks that you will drive past that are kind of taking CO2 for various kind of food related, medical related industries, for example. But the two kind of big new markets that we're looking at are in this e-fuels production and kind of novel materials, so it could be novel construction materials. And there we kind of that liquid CO2 has a potentially significant value in those markets for kind of creating onward high value products. So so A and B are the relevant routes for the biogenic CO2, and the next slide we're going to jump into a couple of case studies, a couple of caveats on those case studies. So we've gone for ones where there's reasonable amount of public domain information out there and available. I've got a disclaimer on there saying that we've worked on these projects or similar projects to these, but we're not kind of releasing any of those trade secrets. But it's also worth saying that we have seen many other examples or potentially positive examples, including from the pulp and paper sector, where there are positive IRRs, even if we're not necessarily able to share those direct. So case study A here. So we're looking at those two primary routes for biogenic CO2. So this is the example of Stockholm Exergy. So I started writing this slide a few weeks ago, and the good news, if anyone didn't spot that, is that this project took FID last Thursday, so reached financial close and is going ahead. The project itself, it's run by Stockholm Exergy, which, as the name suggests, is it's a large power and heat provider based in Stockholm, providing power, heat, and some cooling services to about 190,000 households in the Stockholm area. And that was an important kind of underpinning revenue that they had for this project to get the CCS project done. But the base site is there and generating revenue and providing those services. The project is actually piping that flue gas out from the site to harbour, and then is capturing that CO2 at the harbour. So Saipem are involved there as the EPC provider using a Capsol HPC technology. And then that 800,000 tons of captured CO2 is then getting taken to Norway to the Northern Lights project. Also worth noting that Northern Lights Phase 2 also took FID off the back of it. So you're kind of starting to see this chain developing and going forward together as we need to see in CCS. Crucial to the success of this project is kind of the left-hand side of this diagram. This is the ability to stack grants, stack operational phase revenue in order to kind of make up for the quite significant capex costs, which we'll talk about in a moment. But they were able to stack revenue from Microsoft, so a 10-year agreement at 330,000 tons of CO2 or carbon dioxide removal credits per year. So depending on your view of the price, that's perhaps 500, 900 million over that 10-year agreement. You then have 45 additional agreements with other firms for selling those CO2 removal credits. One of the public ones is with the Frontier, so that was 15 million a year for a 3-year agreement. They also stack the government funding, both from an EU Innovation Fund grant, where they're required to move through for certain steps to release that whole grant, and then very, very importantly, just last year, this BECS reverse auction run by Sweden, where they were able to secure about 15-year agreement for just over 100 million euros a year of operational phase revenue for the project from that process. So the entire revenue stack is somewhere between 190 and 250 million euros per year that we can see, and there may be some other revenues in there. So it's quite a significant revenue driver for a district heating plant of this size. In terms of the capex, so we certainly see it's quite sizable capex. So the EPC contract itself was I think a little over was over 600 million euros, and the total capex seems to be estimated at above 1 billion, so perhaps up to 1.1 billion euros for that. And it is worth noting that when we saw some capex estimates back in 2022 when they were applying for the Innovation Fund grants that were more in the 500 million ton range of that. So we did see a big increase in the capex cost that they estimated as they moved through the project. So this project is, it's fairly simple in concept. There's some big numbers, big costs, and big revenues involved in it. But you're really taking the CO2, capturing that with as Katarina said, a kind of a fairly established technology. Although Capsol are, I think, a newer player in that. But then directly storing that CO2 to generate those carbon dioxide removal credits. A different route, so looking at route B, where you're taking that biogenic CO2 and then utilising that CO2. So this case study is where we're calling this kind of a generic liquid wind flagship approach. So some key points here is that you've got a host site, a CO2 source, and they're capturing that flue gas. There's a partnership with Carbon Clean that Liquid Wind have, so they're able to kind of provide capture to the project rather than the host sites necessarily having to source that themselves. Typically, this is a project sized to about 130,000 tons of e-methanol. You're talking about 230,000 tons of captured CO2 for that. But then, importantly, in order to derive the e-methanol, you also have to be, it's a more complex process. You have to be bringing hydrogen in as well, and in doing that, liquid wind, as the name is, doing that with renewable energy and electrolysis. So even though you're capturing a small amount of CO2, the estimated capex is probably quite similar to the Stockholm XG case. So it's a smaller CO2 volume, but a more complex process. So it could potentially be even higher, depending on your cost assumptions for things like the electrolysis. The revenue range is similar that we would see for this, but it is highly dependent on getting that premium for the e-fuels, for the e-methanol. So the likes of Maersk, Stena Line, DFDS have all talked about partnerships and working with liquid wind. But if you're able to get that significant premium, so above the 400 or 500 euros a ton for fossil methanol, up to 1,000 or 1,500 euros per ton for the e-methanol, then you get into that revenue range of estimate 105 to 220 million. It's also worth noting for these kind of projects, there's also potentially some government funding. So examples we see for liquid wind would be the EU Catalyst partnership, where they're taking equity and also providing some grant funding, and the Swedish Climate Leap funding. So not quite as large as the government funding levels we have on Stockholm Exergy, but the projects also haven't got as far yet. The last point to note in terms of the economics here is, yes, you need very good offtake, but you also need to be able to secure low-cost hydrogen. So liquid wind are talking about doing it themselves, but if you've got low-cost renewable energy coming in, then that's what will allow you to perhaps get your hydrogen cost down to, to let's say $4 a kilogram, or even lower than that. And those are the kind of numbers you'll need to see to make this project work. So low-cost hydrogen will be a key success driver. And then the last point to make in terms of the technology here, there are these kind of interesting, exciting opportunities to bring in, to optimize. So when you're doing the electrolysis, you're creating kind of spare oxygen in that process. So the hydrogen's coming out, but also the pure oxygen. And you could use that in a kind of oxy-combustion process to lower the cost of the capture. So bringing together those technologies could be an interesting use case, a good way to lower the overall cost of that CO2 capture and the system if you combine those together. So in order to leave time for the Q&A, we've just got one final slide on success factors, which I'll talk through quickly, and then I'll switch in. So number one, we would say to keep track of the emerging technologies. The existing technologies are proven and improving, but some of those emerging technologies, for example, the ones that Katarina was outlining, can provide the potential for a step change in lower cost. Picking your value chain position. We're seeing successful models developed right across the chain, but for biogenic CO2 owners, that can go from as simple as selling the flue gas across the fence with utilities, right through to some players who are interested in getting completely involved in those e-fuels markets. So really kind of pivoting into new markets. And there's not only one choice that will work. That there are many value chain positions that you can take as that biogenic CO2 owner. Don't just take the first offer. For example, considering the route to market capabilities of the offtake of your CO2 will be important, because it's not just the revenue levels, but the success likelihoods, which will vary from those offers. And we certainly have seen some players locking in with off-takers, exclusivity on those, but little upside. Revenue stacking will be important, as we've seen, including revenues and grants, but also worth flagging that the current revenue levels that we might see from, say, CDR credits, there is a risk that they could decrease if you're taking a wait and see approach. So sometimes those offers might be better today than they would be in a few years' time. And lastly, we talked about it a bit, but not too much, but infrastructure can be a key advantage. If your site is well located, good infrastructure options will tend to have a competitive advantage. So that's it for the slides. Thanks very much for listening in. So we're now into the Q&A side of things. I've been asked to run this bit as well, so give me a quick moment to read through. But I'm going to go with the first one here. I can see in the example. So the limitations of the different technologies seems like one. So what are the limitations of those technologies, and do those limitations narrow the selection of choices dramatically? For example, on the PSA cryo, possibly not being feasible for a pulp mill because of the CO2 content levels and MOS sensitivity.
I can answer that. Yeah. So for PSA cryo specifically, there is a trade-off between obviously CO2 levels in the flue gas, but also the scale at which you're capturing at. If you're below 10% CO2 in your flue gas, then no, you will not get a reasonable energy spent per ton CO2 out of this. If you're approaching 15, we can start discussing it, especially if you're capturing at larger scales. And by larger scales, I mean possibly where the amine and HPC end their standard packages. So from 400 KT upwards, it might still be worth looking at cryo PSA solutions, even if your CO2 content is lower than the 20, which is probably the optimal point. So there is a trade-off between scale and CO2 concentration, definitely. And I think there is a benefit in pulp mills here because you do have large volumes in some cases. And depending on which stack you choose to capture from, you might be able to blend the flue gases to optimize the CO2 content of the total combined stream. As for the MOF question, the limits for sulfur dioxide and NOx, I think, are not anything that would require additional cleaning compared to other systems. I'm not sure where the information comes from that they are very sensitive to impurities. That's not my, that's not what I've heard.
Okay, thanks, Katarina. Okay, so I will move on to another one. There's another one in the chat here. So how do you see the negative emissions from bio-CCS being accounted for under the ETS or under kind of LULU CF, so land use change and forestry? And I think it is a very complex. The accounting for these emissions is and will be complex, and is an ongoing. There's a lot of ongoing discussions on those at various levels. But I think we see it in kind of two places, and I think the our perspective is that if you look at the emissions from a fossil power plant, let's say that a company has, it is typically accounted for twice. In that it's both counted as the emissions that a company has and it is as reported, but also the country is also reporting those emissions. So if you have CO2 removals, for example, and you're capturing those CO2, it potentially also makes sense for those to be counted in both of those different registries. So both the CO2 capture that's occurring in a country as being reflected in that accounting, but also companies being able to account for that. And what that allows for is then the sale of those credits without impacting what's happening at a governmental level with CO2 emissions in countries. So I think we see that as probably the most likely route for that accounting to proceed down with biogenic CO2 that's stored. There is then another question that I can see. So the examples mentioned are from the heat and power sector. And actually that has some worse prerequisites for carbon capture than the pulp and paper industry, and one example being given potentially reduced operating hours. And we know with Stockholm Exergy, for example, it's not going to be a year-round CO2 capture that's available because frankly speaking, the heat provision is not needed in Stockholm through the summer. So do we have some key reasons from the panel about why the pulp and paper industry has not moved yet or has not been so kind of front and center yet? So I'll ask, maybe I'll ask Dave to come on this one first, and then I'll turn over to Ulf for his thoughts.
Yeah, I mean, I'll refer back a little bit, Stuart, to the poll at the beginning of the call, where I think it was only 2 people felt that the capital was a key question around this, because for me that would be one of the main points. This is such a capital intensive industry with so many investments and so much need for additional capacity. It's not a matter of not being able to get the capital, it's just a matter of being able to put where to put that capital. And I would have felt that was actually a key reason why this has not moved forward faster than it has done already. When we look at some of the work that we've done in this area, we can see incredibly attractive potential assignments, but in the end, things have moved a little bit slower than we would have thought. And I would have agreed with Thomas's as with Stefan's point on this, that potentially it's lack of capital in those kinds of areas. I don't know that Ulf wants to add to that.
Yeah, but I also think that there, I mean, as Stefan writes here, there are other options, for example, lignin extraction and methanol, bark, etc. So there are options to remove carbon from the system, and those have to be accounted for and compared with carbon capture, of course.
Great. I think we are through on time of the 45 minutes. I can see that we are having some more questions still dropping in. I think given we set this up, perhaps we'll, there's one more question I think that we did have in earlier before we hit in the session. I think the others will have to come back to, and we'll undertake to get back to those people individually. So the question we had here is maximum percentage of impurities. So one more for you, Katri, on the technical side, in flue gas, in particular around oxyfuel. So wondering if the impurities in that flue gas are in the process of being a blocker in any of the projects we've seen.
So the oxyfuel itself is not really a limitation here. It's just you're burning fuel with excess oxygen. The cleanup steps following that, whatever impurities you have in the flue gas, will be more set on what you're intending to use the CO2 for. If you're using it in the utilization process, then you would have to clean it to match those specifications. If you're storing it, for example, Northern Lights have extremely stringent criteria on the impurity content that they will accept. So you would then adapt the process steps post combustion according to the final specification of your product, the CO2 in this case. And we've seen everything from very complex cleanup steps and in several steps to fairly straightforward ones. So it's not really a one answer to one question kind of thing. It depends on the final purpose of the CO2.
Right. Okay. Thanks, Katri. I think given the time, we're a couple of minutes over, so not too bad, but we'll let everyone get back to their days. So I'll just wrap up by saying, thank you everyone for coming. The contact details are here. We've put them up, so do reach out to myself, Katri, Ulf or Dave, for any follow-up questions that you have on this. We do have, this is part of a webinar series. We tend to have one of these webinars every month or 6 weeks on kind of similar energy bioindustry topics. So do keep a lookout for that, as well as our Aphrion strategy podcast. So most recently we were talking to Dan Dieterman, the president of Cargolation Transport, and Tom Strang on the Carnival Corporation and the Maritime Affairs. So lots of kind of good strategy work ongoing as well. So do tune in for that podcast. But thank you all for your time, and hope to see you at the next one. Bye-bye.
Thanks very much.